Okay, now we're going to talk about systematically about how the ideas we've covered in the first few introductory clips play out. So, vector function. F of x, y, z is just a function, f of x, y, z, whose value is a vector in three-dimensional space. And we're going to call that, we're going to denote that vector by m of x, y, z times I plus n of x, y, z times j plus p of x, y, z times k, where m, n, and p are simply three different functions of x, y, z. The value of m at a point gives us the I component of our vector. The value of the function n gives us the j component. The value of the function p gives us the k component. Without going into complete detail related to definitions of a vector and so forth, we can simply say that, for example, fx of x, y, z equals mx times I plus nx times j plus px times k, where m, n, and p, mx, nx, and px are evaluated at f, y, z. So it's a fairly straightforward process if we're given the vector function, the components of the vector function, to find the components of its x derivative. And we can also just kind of quickly write out the fact that fy equals my I plus ny j plus py k, and that's fy, and fz equals mz I plus nz j plus pz k, where these are the obvious y and z derivatives of our component functions. A simple example of a vector function that, however, has a couple of important properties and is related. A couple of important properties related to properties of important functions. Let's just let f of x, y, z equal xi plus yj plus zk. Note that our function up here should have an arrow over it indicating that it's a vector function, and so should this one. Now this vector function is going to have a value. It's going to be a vector that's simply equal to the vector from the origin out to the point x, y, z. So if we graph the function at a point x, y, z, and I'm just going to graph this in 2 dimensions for convenience, but it could be extended to 3 dimensions very easily. So let's just say we're in the xy plane. Then the vector xi plus yj plus zk would just be this vector from the origin out to the point. However, we associate this vector with the point. We don't consider this vector to be rooted at the origin as we would with a position vector. So this is a vector field rather than a position vector. So f of x, y, z is associated with x, y, z. It's not a position vector. Rooted at the origin. When we sketch this vector, then, we don't sketch it with its initial point at the origin. We sketch it with its initial point at the point x, y, z. So now that function is going to be identical to this vector, that is the vector representing the function is identical to the position vector, but it's rooted at the point. So that if we were to depict a bunch of position vectors, let's have some at points closer to the origin and some at points further from the origin. Okay, the position vector at this point would just be this. That would be equal to the vector xi plus yj plus zk, but it's no longer a position vector, so we're going to take a vector of this direction and magnitude and tack it on to this point. And similarly, at this point, we take our position vector and so forth. Well, that one is named very well. The thing about all these vectors is they are located at the points, and for the example of this function, they all are pointed directly away from the origin, but the further we get from the origin, the bigger they get. So that if we're at this distance from the origin, our vector function will have a value like this. Now, one interpretation of vector functions can be as force fields. A force field that had these characteristics would get bigger as we move further away from the origin. There's no physical force field that will do this, at least not over all of space. It would take an infinite amount of energy to set such a field up, but we don't want to talk necessarily about the physics of this thing. Just that this can be kind of an interesting example of a force field because it depicts a field that's directed away from the origin. However, that's about the only real useful characteristic of this field. Now I'm going to modify that definition slightly. I'm going to define a field f of x, y, z equal to, let's use this, xi over the square root of x squared plus y squared plus z squared plus yj over the square root of x squared plus y squared plus z squared, and then plus zk over the square root of x squared plus y squared plus z squared. Now this is getting, this is actually kind of an important field. We could write this as a multiple of the field we used in the previous example. This would be the square root of 1 over the square root of x squared plus y squared plus z squared times xi plus yj plus zk. And if we sketch this field and think about what it would be like, and again we're just going to do this in 2 dimensions, but this would extend very naturally into 3. So if this is the x and this is the y, at a point we still have the vector xi plus yj plus zk. However, we're dividing that vector by the square root of x squared plus y squared plus z squared. If we think about it for a minute, this is just the magnitude of this vector. So that this is a unit vector